Hello, and welcome to my presentation for MRTB PMA titled Song Recommendation Engine from Spotify. The objective of this notebook actually is to create a song recommendation engine for Spotify by using machine learning. The main goal for a song recommendation engine is actually to increase the listener or customers' Spotify application usage. So the objective of this notebook actually is split into two: to identify what is the proper machine learning algorithm for music recommendation, and to create the ability to recommend songs with highly similar features to the end user. So we'll go through these steps in this notebook: importing libraries, extracting data from Spotify API. In this example, we'll be using a Spotify playlist called Biggest Playlist Ever that contains more than 5,000 songs with various genres and song styles. We'll be using Spotify API to loop through and pull the data by using client ID, client secret, and the get API function. Then we'll go through data understanding, prepare the data, exploratory, data analysis, EDA, and also model building and evaluation. So to answer specific PMA MRTB 1153 PMA question, this table of content actually shows what to refer to for each of the question. So first, we'll import the specific libraries needed. The important one is to install the Spotify. This is what allows us to use to pull through Spotify API data to get our initial playlist songs and its features. So we'll extract the data from Spotify API. We authenticate, pull through, and get each of the song or tracks from the playlist, loop through and get each of the audio feature from each of the songs, and put it into one data frame, and we save it to CSV so that we can pull it at any time that we want. Next, to understand the data, actually the feature underscore tracks, the data frame that will be used, has around 21 columns. So the individual definition of the column with detailed description are listed here. So these documentation actually can be obtained from Spotify developer website. So it shows all of each of the individual columns definition of data. Once we get the data, we will prepare it by before performing EDA. We'll prepare the data by removing unused columns, check if there's any null value, remove if there's any null value, check any duplicate values, remove if there's any duplicate values, check if all the categorical columns are encoded properly so that we can train our model, and then we'll choose 3 random rows of data to be splitted into our testing data. So these are the data in the raw form, the way that we pulled from the Spotify API. So we'll perform the removal of unused column. We'll remove these 9 columns, and then we'll check if there's any null values and remove. So there's 2 null values, so we'll remove those. We'll check if there's any duplicated values, and also we check if there's any duplicated track and artist column values. So we'll go ahead and remove those. Next, we'll check if the categorical columns are encoded properly. So key, mode, and time signature are all encoded properly. Key are from 0 to 11, mode 0 and 1, time signature 0 until 5. Lastly, we'll choose 3 random data to be split into our test data. So first we'll shuffle the data, and then we'll split into the 3 data to be used as our test data, and the rest will be our training data. Next, we'll perform an EDA. So EDA will check the descriptive analysis of the data, plot the distribution of the continuous data, check if there's any outlier, if it's a normal data or not. Then number 3, check the proportion for categorical data. And number 4, perform correlation check to check if there's any feature columns that is collinear or multi-collinear. First, we split the train data into its the data that we're going to use for the model and the track and artist column. Then we'll perform the descriptive data. So these are the summary of the descriptive data of the training data. Next, we'll plot the continuous data distribution to check if there's any outlier. To summarize, there's no significant outlier seen in all of the feature columns. Majority of the column is normally distributed except for speechiness, acousticness, instrumentalness, and liveness. So the skewness value are displayed here and summarized in the summary below. Next, the proportion of the category data is shown here. So to summarize, key number 3 actually has the lowest proportion out of the key category. Mode is relatively similar, and time signature actually have 4 has the significant amount of data. Next, we'll perform the correlation check, and it shows here that to conclude, there's no feature columns that are collinear with each other, even though we have up to 0.7 value of the Pearson correlation between loudness and energy, but we still don't consider that as collinear. Now we are ready to build our model. So first, we'll perform the distortion check to see of the k-means algorithm, the unsupervised machine learning algorithm that we'll be using. So we will check if what is the proper number of cluster for the k-means algorithm. Then we'll take this, we perform we scale the data, and then we fit the model, the training data to the model and obtain the cluster label. Then we perform PCA, principal component analysis, to visualize the cluster from multi-dimensional data to the first and second principal component. Then we'll prepare the test data, apply cosine similarities function, and rank the recommendation songs. So from here, we can see the elbow actually start at the k equals to 8. So we scale the data to the pipeline and actually put k-means equals to cluster equals to 8, and then we train the data. Then we'll train the PCA to get the first and second principal component. We'll put everything together and we visualize it in this scatter plot. So as you can see, there are 8 clusters available in the plot, each labeled in their individual colors. Next, we will split the test data into feature and song, similar to what we did with the train data. Then we'll predict by using the model that we've done for the training data, what will be the cluster for the test data. Next, we will put in, once we identify the cluster of the test data, then we need to a way to rank what are the songs that will be recommended based on the similar features. So what is the similar function that we use is cosine similarity. So for song number 1, we'll perform the after we get the cluster label, right? We perform the CDist, which is the cosine similarity function, and we obtain a data frame contains the song that is recommended based on song number 1, the top 5 recommended song as follows. This is the result for song number 2. This is the result for song number 3. So after going through the recommendation model, each of the song, even though it is categorized in cluster number 1, it has a different recommendation song based on the cosine similarities. So since the model is an unsupervised machine learning model, the only way for us to validate the recommendation engine is through the real-world application tests and also gather listeners' feedback. To conclude, the objective to identify a machine learning algorithm for music recommendation is achieved, which we use the k-means and cosine similarities function. Next, the ability to recommend songs with highly similar feature are also demonstrated in the notebook above. Lastly, based on this definitely will help to increase listener of Spotify application usage by the recommendation of songs using machine learning. Thank you.